we are sorry, we are applying some mathematical operations. Those, see, these are the modulated convolves. These are mainly given with respect to the DSP processors. These are very, very common for that application specific. These operations we just apply on our input data stream, and then this model handles those input data, related dependency on them, and whatever mathematical operations we have to apply on them. That's all. So if the data related operations that is really dependent, then we have to schedule them maybe in some multiple layers. Here you can see that here A, B, on top of that you are applying a mathematical operation class, and C and D that is some other operation, maybe minus. Now since these multiplication that requires output of both of them, it is not possible that you schedule this multiplication also in the first level. So based on your data dependency, only that hierarchy is maintained, and based on that, you actually the modeling technique schedules the algorithm, schedules the operations. So that is the concept of data flow model. Of course, the data flow can be synchronous or asynchronous. Now, this is one limitation, or we should say the data flow model is one example where FSM or finite state machine state change based on some transition may not be effective. That is one limitation. The another limitation is when we closely observe state chart. Remember, we talked about communicating FSMs. Now, specifically for state chart or FSM type of scenario, these communication, the sharing of variables, sharing of information is taken place with the help of shared memory. If you remember, at that time we discussed how the message exchange are taking place, information exchange was taking place between two communicating FSMs, and there we talked about two strategies, two approaches. One is shared memory and another is usage of shared message queue. Now, usage of actually message queue, I should say. Now, in case of state chart, the convention they follow, they actually use shared memory for this message exchange, for communication between multiple FSMs. Now, this is not suitable in case of distributed applications. That's why that is a limitation of state chart. The state chart is not suitable for distributed scenario. But as you now probably have the idea that when we are talking about embedded system, embedded related applications or cyber physical systems, we are not only concerned about a single cyber physical system or communication between 2 or 3 cyber physical systems. We are concerned about maybe a layer of cyber physical systems, and underlying there you need to communicate between multiple FSMs or multiple state change relations. So they are, in that way, distributed applications, handling of distributed applications, we should say, are mandatory, and that's why SDL or specification and description language came into picture, where it shows basically the concept of very similar. That's why we are quickly discussing this type of models. See, if you remember, this was our discussion about finite state machine. Maybe this is one problem specification that we have mapped to these states. These are 5 states, and G, H, I, J, they are the transition conditions or the guards we have defined. And this W, X, Y, Z, they are the action based on these guards. Also, if we, you understand, these are guards and actions. So maybe you have modeled your specification to such type of similar finite state machine. Now, when you have multiple such machines, it is not possible through state chart in distributed scenario to make a communication between them because the problem with the shared memory concept. So here the concept used is the usage of message queue. The idea is you can see if this is the FSM, if this is your process, then these process either these part is quite similar, only the representation is different. You can see this in this process, the process P1, where in FSM this was your representation. Here this is your representation. You are actually considering each and every transition separately. So here you can think this A to B, this is one transition. There, this is your guard. This is your input condition. You can see these are the symbols representing the SDL language, and this is the output. This is the output, and then based on this input, setting of output, after that, along with the state change from A to B is taking place. Similarly, B to C and so on. And here in the last condition, from E to A, this transition is taking place either by just with the transition condition getting satisfied, that is K, if K is getting satisfied or F is getting satisfied. In both the cases, the transition is getting taking place from E to A. Only difference is that in case of transition condition K is getting satisfied, we are not setting any output variable, or we are not setting the value of our output B, output signal B, output variable B, whatever it may be. But in case of if the transition from E to A is taking place due to the when this if transition condition, if guard is getting satisfied, at that time we are setting this value V. Okay. So this is I think only this is just a change of how we are representing the state and transition conditions with a few typical, what to say, images, a few typical symbols. Otherwise, the concept is very similar. But the difference lies here in this SDL inter-process communication. This is the main requirement or main, what to say, difference between SDL and FSM based state chart. So there we remember we talked about shared memory. Here we are talking about queue concept. Queue concept means queue means that is queue works on first in first out mode. That means here is a process and this process is associated with some queue. Similarly, process 2, process 3, you can see each of these processes, they are associated with some queue. Now, in general, when you implement queue type of structure, what we use different functions, that is NQ or DQ. I'm talking about in normal data structure, maybe programming and data structure you know, so FIFO concept you will understand. So mostly process 1, it will input its signal value in this FIFO queue, and process 3 will as and when required, it will fetch that signal and it will consider the transition based on that signal change value. So the idea is here the communication is totally asynchronous. It is not that for this communication there is any requirement or that the two processes should be in sync and then the communication will take place. Here the process communication is totally asynchronous. Process 1, whenever there is a state change or a value change of any signal, and it knows that signal should be communicated to some other processes, maybe process 2 and or process 3, that value is getting stored in that queue. And with the FIFO concept of queue, first in first out, whichever signal is coming first is getting out first. So process 3, process 2, whoever it may be, it is taking its respective queue and fetching out the signal values and considering this transition based on the signal change signal values. So that means if we go to a higher level, any process transition is getting the communication as defined is taking place maybe based on the destination process value, destination process ID. That message, this is the process ID, destination process ID. So for which process it is destined to, or via some channel. That is also a concept that you are thinking about some channel, dedicated channel between different processes, and that communication is taking place. So these are two notions, both are possible. So when we are talking about process interaction diagram, then we are thinking about the channel through which your message exchange is taking place, and what will be the message that is going from process 1 to process 4. Same for some other processes. So that means, and another concept here is SDL maintains a hierarchy. That means you think whenever you have written your elevator problem, there you have a if you think we name that one is request resolver, another one is maybe unit control or something like that. Now this unit control, you can think about it's a big process, maybe one block. Among them, among that big process, you may consider different sub processes. So those are the sub blocks, and based on that, the hierarchy is considered. That means whenever you are thinking about a system, that system is basically you are thinking about different components or communication between different blocks. Now these blocks may be a single isolated process, or that can again be divided into sub-blocks or sub-processes. So blocks at the highest hierarchy, we consider it as systems. Blocks at the lowest level hierarchy are called process interaction diagram. Why that is? Intermediate process blocks, we consider them as the sub-processes. And the final layer, final lowest layer, that defines how these sub-blocks they are connected. So maybe this is the hierarchy. You can see this is a system which is based on sub-components and some multiple sub-components. And when you are reaching to this sub-component, you are actually defining how these processes they are actually communicating to each other. Okay. Along with that, SDL also have some added features like timing, reset, set and reset values. And then you come to this practical example. How you are actually going to map or model a practical system that requires to handle multiple sub-layers. Now here you can see this is a system, and which is consist of a practical system, computer network, where you will think of processor, processor B, processor C, router. All these parts of the computer networks are there, and they are typically connected with some communication requirement. Okay. So in this case, when we are talking about HDL, we are thinking about different blocks for processor A, router B, C, and within that block, we are actually considering sub-components who are getting mapped to the sub-processes, underlying processes. When we are reaching to the process part, we are again realizing that process with the related state transitions and how these processes are getting connected. So basically, we are breaking our system to sub-components. Each component, our final level is getting mapped to such type of processes and process interaction features. So this is the main concept of SDL in comparison to FSM or state chart. State chart is basically nothing but hierarchical FSM. So in comparison to hierarchical FSM or state chart, SDL is having the advantage of using this message queue, and this message queue is giving the capability to handle communicating signals in an asynchronous way. So this is typical another way of thinking the modeling of our process networks. But where is the limitation in this case? Of course, this is good for distribution scenario also, and the lower level we can also handle in the proper state along with the state transition conditions when we are breaking them into smaller blocks. But the advantage of SDL is again the disadvantage of this process. Of this modeling technique. That is the FIFO queue. Okay. So what is the limitation? The limitation is that when you are actually, the concept-wise it is fine. Concept-wise, if you go back here, wherever any process is actually creating a signal, it is storing that to a particular another queue related to a particular process, and process C is fetching from that queue. But the problem is, if process 1 is creating too much signals within a particular time frame, then how much that too much will be? How will you model prior? That means it is the limitation, or it is the challenge to decide the size of this individual SDL queues or message queues. Because if you cannot model that, if you allow too much of size for these queues, that means you are actually doing some very worst case analysis, and then you are not doing proper worst case analysis, and you are just arbitrarily allowing huge size of this message queue. That means whenever the signals are coming, this is good in general, but when you think about embedded domain or CPS scenario, we are basically working in everything in a constant environment. We have some limitation in terms of timeline. We have to finish the task within a timeline. We have some constraint in terms of memory. We have a constraint in terms of hardware resources. So everything is constrained here. So it is not possible that you are actually allowing very huge number of huge queue sizes for each and every process, because there is not that there was one or two processes. It may happen, maybe you have already seen, right, in our RTOS scenario. RTOS scheduling, you have seen that so many processes you have to handle according to their priority and their interaction. So that means that is not possible that for each and every process you are allowing a huge amount of only SDL queue. That will incur huge memory overhead. Again, very small amount of resource allocation or message queue size allocation will lead to, you can understand, overflow. Maybe all the processes, maybe if some process is sending too much signal to another process, maybe process 1 is sending too much signal to process 3, then at that time it will after some time, maybe all the signals, all the communicating messages cannot be sent to the process 3 due to the overflow of this FIFO. So this is a main challenge when we are talking about, main limitation when we are talking about FIFO. That means how we will predict the safe upper bound on the length of FIFO queues. Okay. In actual hardware system, implementation, actually FIFO should be a finite length, but it is difficult, and you have to should have a very detailed prior knowledge of your system specification, of your design specification, to calculate this safe upper bound. Okay. Next, we will go to Petri. Is there any question up to this part? Any question? Let me see. Okay. Next one is, so we have seen that Dataflow model FSM is better to handle the event-driven scenario. Dataflow model is for handling only data flow related specifications. Then comes the SDL, where on top of a state chart, we are getting the advantage of distributed domain handling, distributed scenario handling. Now then comes the Petri, another very known and very popular modeling technique nowadays, along with FSM. Why? Because the Petri, they do not assume any global synchronization. That is not required. It is suitable for modeling distributed systems. Along with that, we will see some examples and we will see how it helps to model concurrency properly. Okay, let's see how it looks like. This is how Petri looks like. So in this Petri part, you can see there are two things. You can see maybe one is circle type of thing and one is rectangle type of thing, and some flow arrow associated with that. Maybe you can think as of now they are showing some directions. So here, and a token that is placed inside this circle. Now Petri is based on some place and transition. What does it mean? Place means this place where the token is residing, and that is basically defining the state of your system. These tokens state of your system, and this rectangle that symbolizes the transition condition, for which these tokens may change its state from this circle to this circle, or may return in this particular state. So that transition condition is given by this rectangle box, whatever we are entering in the rectangle box. So we can understand that when we are thinking about state transition condition, those may come from some events. That means due to some event, the state of this system where the token is residing may change from this part to this part. Okay. So similarly, again from this event, this token maybe from here can change from this part to this part. So this is a basic idea of how Petri looks like. Now we will see these few properties of Petri, why it is important nowadays. So maybe you can work with this example and you can go see when there are different types of transition conditions, how the state is changing. And this is a very important example, because if you actually follow this direction, if you work out this example, you will see how this Petri, this modeling technique is useful to avoid collision. Okay, or actually at least detect collision in your modeling scenario. So just go through it by your own letter. Just with this whatever conditions given, change the state of this token and see where it is going, and where in case of multiple tokens, how collision can be detected with this modeling scenario. Okay. Now we will define it more formally. Okay. When we are talking about a net, Petri net, what does this net mean? This net means it is based on C, means C is some condition, E is the event. Okay. here it is written, C is called conditions, E is called events, and F is a flow relation which can be defined by this way. That means when you are considering some pair of event and conditions and some condition and events, and that union that will define the actual relation, and that is called the flow relation. So when we are talking about Petri, Petri is by the name of the proposer and the net. When basically we are dealing with a net. Now this net is consist of these main things. Now in this diagram also, if you go back, you have seen that CEF. That means this is the condition. These are the conditions maybe what we are writing in the rectangle box. These are the event. Condition event. Sorry, these are the event. These are the condition. Condition means that means where you were placed, your token is placed, and the flow relation, in which direction you may move, or if for a particular pair of condition and event, if the flow relation is getting satisfied or not. Okay. So based on that, we are defining a term called pure nets. Pure net means, you can see we are defining X as a member of condition and event union set, and this dot X, that is basically the set of preconditions. That means that is where this Y is based on some condition, that is a precondition for which some flow relation and some post condition is getting satisfied. Okay, so this is called the dot X is the set of preconditions. Similarly, this is the set of post conditions. That means for some condition X, some post condition X is getting satisfied for some flow relation and some other conditions. So this is the concept of precondition and post condition. Now, why we are considering a net a pure net? A net is called a pure net if it doesn't contain any loop. Okay. So how will we detect the loop? With this condition, if this is true. See, this is one AND condition. That means for a particular condition, if any event and through some flow relation, if any event is getting satisfied, and for that event, if that again that same flow condition, with some event and some flow relation, same flow relation, if the same condition C is getting satisfied, if both are true, then this pair is called generating a loop inside your net. And if there is a loop, we cannot call this as a pure net. That means in pure net there will be no loop. Now in practical scenario, can you give one example why this detection in our modeling is important? Anyone? Anyone? Can you give me any example why in your modeling technique it is important to detect this kind of loop, or at least to check whether the desired loop is there or not? Why?
The system could get stuck in a loop.
Pardon?
Ma'am, the system could get stuck in a loop. And
yes. So in general term, what do we call it? Computer science term, maybe in terms of OS, we call it if there is a possibility of deadlock or not. Okay, so if some condition is actually getting satisfied and some event is occurring, and to get some condition to be satisfied, if we are waiting for that same event, so that means there is a possibility that that system may be incorporating some deadlock. So for deadlock detection, this loop detection is very important. Okay. Next, the formal definition, there's another definition that is called simple net. Okay. If no two transitions, a net is called simple if no two transitions T1 and T2 have the same set of preconditions and postconditions. Okay. Now this is called the simple net, or sometimes simple nets with no isolated elements. That means all the events or all the conditions, whatever you can think, they are basically connected. So that is called condition or even net. So this condition even net is basically the simplest form of Petri net, and we will see a few, improved version of this simple net, which are mostly used in embedded system modeling or CPS modeling. So from condition or even net to, we come to place transition net, where we can see the number of tokens per place is called a marking. That means for a particular place, that place may be not a single token holder, or that may be a multiple token holder. That means when we are considering, go back to this part maybe, when we were considering, this is the state. So there we have seen that this is a single token holder, right? That means at this time, this system can have in a single state. And that's why from this single state, if this condition, you can see this condition, whatever this condition was there, if that is getting satisfied, this system will move to another single state. Okay. So this is the concept of condition even net, the most simple net. But in case of place or transition net, you can see there are multiple tokens possible. Okay. With that multiple tokens possible, when any transition condition is getting satisfied, maybe this is a TJ, that is one transition condition, that transition condition will actually consider some number of states, that is some number of tokens, that will be decided by the weight of this associated age between this place and this transition. That means here you are having 3 tokens. It doesn't mean that when any transition is taking place, it will consume all possible tokens placed in this state or placed in that cycle. It may, since this age weight is 1, it will actually consume only single token. That means, and it will generate another, some token, some post condition. These are the preconditions and these are the post conditions in this, output cycle maybe. It may happen these placeholder, these tokens, they are actually connected to some other transition conditions, where these transition conditions, due to these events when this taking place, based on these transition conditions, the state change will take place or not take place. Maybe you can think in this way. This, when I'm talking about this tokens, you may think these are the transition conditions. Those are maybe output of some events. these states which are actually based on these conditions, this that will I mean, what is it? Because yes, before transitions, after transition. Let me think 1 second. There's a number of tokens. So transitions, yes. When this transition is happening, the state number of tokens, it is getting reduced from 3 to here. Again, based on this age weight, it is reducing to 1. So this is the concept of place and transition nets, where you are associating some age weight, and there are two properties, and marking. Marking means how many number of tokens are possible in that particular circle or step. So these are the typical types of Petri nets. We'll see one practical example with this Petri net, and then we will see what are the properties we should analyze to make it more prominent modeling technique. Another one quite similar, just predicate or transition net on top of place transition net, where you are using some ID, so message ID associated with each of the tokens. So some typical, here all the tokens are very similar, but in case of practical scenario, you are using adding some practical some associated ID with these tokens. So these are the types of transition nets or types of Petri nets. We will see one example for each. Then I think that will be clear. Wait. Okay. Now see just this example. This is a very, I'm just doing the slideshow, but there is some irritating sound associated with this. This is a slide taken from Professor Quisling. So you may go through it because this is a very clearly written slide, and it is very good to understand. Just you think in this way, that when we are talking about state transition diagram, here STD means state transition diagram of a finite state machine. Okay. What we do, we are considering for, this is the example of electronic fund transfer. That means you are entering few digits, maybe you are entering your ATM pin, and digit by digit, and once all the 4 digits are given, then you are pressing OK, it is getting approved or it is getting rejected. Based on that, you can proceed for your next operation. Okay. Now you can see, according to this state transition diagram, that when you are entering one digit B1, maybe if your pin is 11234, okay, 1234, you are going from starting from 1, you are adding 1, and you are pressing OK. Of course, one digit is not acceptable, so it is directly going to the state rejected. Similarly, if you are going to enter 2 digit or 3 digit, then you are anyway pressing, I mean, somehow by mistake or something, then it will go to this rejected state. Similarly, if you go up to 4 digits, and if you have entered them and you have pressed OK, so these are the conditions, and this OK press, that is the event. Then it may happen, then there is a match. This part is not shown. There is a backend, maybe some software that is checking whether there is a match or not, and then it will be rejected or it will be approved. So that is the general idea of how we understand the state transition diagram in FSM. Then comes the Petri net. Okay. So what happens in the Petri net? Now I will Okay. You'll see there is some noisy sound, but how they have done it. So if this is your initial step, from there you are entering your tokens, or that is the step. So you have entered the first digit, and then second digit you have not pressed OK, it is going to this path. Wait. Similarly, the third, fourth, then OK, if it is approved, it is going to this path. So this is how the state of your token is changing based on the intermediate transition conditions. So this way you can actually represent your specification with this Petri net scenario. Now there are few more examples. You all can go through it, but what is important is, if you see, this type of, when we are talking about net structure in comparison to FSM, this type of concurrent path we can think, and there we can see in which way or which state this token is moving. That means this concurrency can easily be modeled with this net structure. Okay. So another improvement is that, or we can say advantage is that, synchronization and concurrency. That means you have multiple tokens in these places, and these transition condition in this E1, it is showing how this synchronization between these nodes can be handled. And after that, if the tokens, multiple tokens, they are taking some concurrent path, that part can also, that states and their state transition conditions can also be modeled. So this way, if you think about FSM or state chart, this is not very easy to actually model with a so easy visual representation or so easy state change. It is not very easy to handle this synchronization and concurrency. This is just for the modeling part. Along with that, PetriNet gives us some advantage of how we can analyze possibilities, future possibilities, or the one thing we have seen that bottleneck possibilities or deadlock possibilities, and another thing is that what will be my reachable states. That means in advance with this modeling technique, we can check whether starting from one state, if or if not, my system can reach to a particular state. Okay. This marking means market is we consider as a state. Now, when we are considering, that this matrix, it is called reachability matrix. Reachability matrix means it shows whether whenever I am my token may be here, I have these possible transition conditions, and based on this transition conditions, if we actually traverse all the paths, after certain amount of time, certain amount of state transitions, what can be my reachability? Or let's take this example. See this. This is the reachability matrix of this problem. Reachability matrix means you can see a few 100 combination. That means this is, you can represent as a matrix where if you have P1, P2, P3, P4, P5 number of places. So these 5 you can say columns, they are actually representing the place values. That means P0 to P5. Okay. And these are what can be the possibility of token can be placed at that possible place. Okay. That means you can see in the first transition, when you are considering P0 as, the token is in P0, that means this is 1 and all the values are 0. Okay. Next, see, this is very irritating. Next, if this is your reachability matrix, it shows that after one transition, your token will go to place P2. See, only P2 is 1. That means at that time, your token will be in this place. Okay. Similarly, after next transition, your token will go to this P3 place. So P3 means here. That means it shows from P2 to P4, this event this transition condition is not getting satisfied, and your token is actually moving to this direction. Okay. So that way, in this way, you are actually following. If you are following this reachability matrix, you can see, you can identify which transition is actually taking place. That means M0 to M1. If your token is now in M1, you can get the idea that T1 has taken place. Similarly, M1 to M2, that means T3 has taken place. Similarly, M2 to M3, M2 to M3. That means P3 to P4, P3 to P4. That means T5 has taken place, and so on. So based on this matrix, there are two ways. From these transitions, actually you can form this matrix. Okay. And from this matrix, you can get the idea what are the possible reachable states starting from this initial marking M0. That's why this is called the reachability matrix. Clear? Now, how it is important? Why is it important, and why should we consider? Should we analyze this reachability matrix? Let's see with an example. So that understood that this M2 is reachable from M1 and M4. So based on these transitions, whatever reachability matrix you got, or the either way it is true, you can identify which are your possible reachable states. We will actually merge with these properties. We will, and in a practical example, we will see how it is effective. Another property is boundedness. Boundedness means, you remember in our place and transition net, we talked about that each place may hold a single token, may hold multiple tokens. Based on that, there are defined types of petfinets. So a petfinet is said to be k-bounded or simply bounded if the number of tokens in each place does not exceed a finite number. That means that is a threshold. That is the maximum number of marking of your petfinet. That means the maximum number of tokens allowable in that petfinet. Okay. Next one is liveliness. Liveliness means a petfinet with minimal initial marking M0. You are starting from a marking, that is M0. Is live no matter what marking has been reached. That means from your marking M0, maybe you are actually analyzing all possible transitions, and then you are checking that whether there is a possibility of deadlock or not, or is there any situation that your token is has got struck and cannot make any next transition. So that means to check your design, if it is, especially in case of a concurrent scenario, if that is deadlock free or not. Okay. So that means we talked about three main properties of petfinet that is important to analyze. One is reachability, starting from any initial marking where you are reaching. Is the liveliness, and the third one is the boundedness, the maximum number of marking possible in one placeholder. Okay. Now you come to this example. Okay, again this sound, wait. Okay, maybe, okay, let's complete it. So if you see, based on this transition T1, maybe I should go back. You have one in a initial condition M0 is given as 1001. That means in your place P1 you have one token, and in your place P4 you have one token. That's why 1001. There is no token in P2 and P3. Now there is a transition T1. That means this transition is actually consuming the token in P1, and it is going to this P2. Okay. Now you have two tokens to the input of this transition condition T3. That means to T3 to get satisfied, it requires two transition conditions. How do you understand that? Let's see, M1, after that, this is a case, M1 is 0, 1, 0, 1. So M1 is telling you that you have tokens in P2 and P4. Then you see after M3, P3, after M2, you are having the condition 0, 0, 1, 0. That is your reachability matrix shows. That your reachability matrix shows. That means to this T3 condition to get executed, you need inputs from P2 as well as P4. Okay. Next, this is T4 is getting executed, and you have the token in according to your reachability matrix 0, 0, 0, 1. That means you have the token only in P4. Now from this reachability matrix, you can analyze that the system you have modeled, these may be bounded but non-live. Why? See, after this, when you have a token in this P4, and if any transition condition is getting satisfied in this T3, then also, any transition even it's getting satisfied in T3, then also to make this transition successful, what you have to get inputs from P4 as well as from P2, but you do not have any token left in P2. Okay, so in that case, these token cannot proceed anymore. That's why this situation of your Petri, Petrinet, you can consider as non-life. It cannot proceed anymore. Okay. Similarly, you will do it in, this will be your job to check this example. You will see for these transitions also, you will get some, go through this slides, some reachability matrix. So there are some reachable states, M0, M1 like that. And you check, and you for each and every iteration, you check for it. You will find it that this example, there is no issue of liveliness. So that way, this is the analysis technique of Petrinet, especially important in concurrent scenario or complex systems, embedded systems, where Petrinet is capable of analyze your model in terms of both reachability, whether you can reach starting from a particular state, you can reach to a particular state or not. Number two, if you are considering that your system is bounded, that means particular number of tokens possible, fixed tokens possible in a particular place, whether with that bounded condition and with a given reachability condition, your modeling technique or the specification, whatever you are analyzing, whether that will remain live or not, that will remain deadlock free or not. So this is one very important, requirement, how Petrinet is different from other existing modeling techniques, and that's why it is very popular nowadays in case of embedded scenario or CP scenario. Okay. So that's all so far. We have two small discussions left that we will do it later. Okay. Both the branches from state D4. Okay, there is some question. D4 have the same input. I think the branch that goes to direct trajectory should not exist. Oh, Rudrajyoti, have you got your answer? You have written something. Oh, ma'am, both the branch.
No, ma'am, it's actually in the previous.
Which slide you tell me? I will go back there.
In the slides, in the first part of the slides.
This slide?
Yes.
Petrinet?
Yes, ma'am. In
This
the
one,
first
okay.
part.
First part. Okay, I will again.
Yeah, the branch from D4 to rejected should not be there because I think OK should be pressed for means both the
this one, right?
inputs to
Yes.
it are OK.
Okay, pressed. Yes, then
Means from D4 for both the branches the
D4.
input is
Yes.
OK.
Okay. Yes, this should not be there. You're correct. Because if this okay, it should go to this direction. Yes, this should not be there. Anything else? Any other question? Non-deterministic example, it is 60. Sudha, can you be specific? I'm not getting your point.
Ma'am, because from that state there are two transitions, like more than one transition possible, so it is a non-deterministic.
Oh yeah, it will lead to actually there are same conditions given, right? The same conditions and same states, and from there it is going to different paths. Yes, that is wrong actually. That should not be there. Anything else? If nothing, then I think that's all for today. There are a few more things I should mention. Okay, I will upload one paper about this Petri and and another and this slide also. So go through that paper. Maybe that part the writing is very clear. I mean follow that paper, read that paper. Then I think it will the reachability analysis, the forming of reachable matrix. That part will be clear. Okay, I will upload this. Okay, if there is okay, another announcement. This Thursday there will be no class. I can take the class after. I mean, maybe that is next Thursday. Okay. Next Thursday means it is 29th. There will be no class this Thursday, 22nd. Okay, you may leave now for today. Thank you.
Thank you.